Okay, so here we're going to take a look at a couple of examples dealing with measures of center and measures of variability or dispersion. So let's see, example 1. College course has 5 tests that are all the same weight. A student scores 74, 69, 85, and 73 on the first 4 tests. The student wants to get at least 80% for their average. So what score on test 5 is needed? All right, well, first off, let's remember what we're doing to try to find a grade average, which would be a mean. We got to add up all the data values and divide by however many there were. So here, what she wants is the sum of the 5 tests to be 80% or higher. So if we set this up, we're going to have to use a variable for our test 5 score. So this is one of the few times when algebra really comes into our course. We're not going to do much with algebra, but this would be one instance. Let x equal the test 5 score. So now if we wanted to find the average of our scores, we go 74 plus 69 plus 85 plus 73 plus this unknown score, x. That would represent the average. We really want that to be greater than or equal to 80%, but let's just set that equal to 80 to get the cutoff. Not really fond of the way this looks, so let's do this. Let's add up the 74 plus 69 plus 85 plus 73. So if we add those 4 numbers together, we should get 301. So we got 301 plus x over 5 is equal to 80. When I see this fraction equals another fraction, I think maybe we want to use cross products to make this look a little bit nicer. So the 301 plus x times 1 is just going to be 301 plus x. 5 times the 80, well, that's going to give us 400. Now I can solve for x pretty easy. Let's just subtract 301 from both sides. And we got x is equal to 99. So it looks like getting that 80% is going to be pretty tough here, because this really means that the student needs a 99 or a 100 on test 5. They need a 99 or higher to get that 80%. So there's a lot of different problems like this where sometimes they say, well, the average of the first 20 students was 80. Then when the 21st student gets thrown in, the average drops down to 78. You know, what did that student score? You can kind of do it the same way. Like, for example, had they said something like the average of the first 4 tests was 70 here, instead of adding up the 4 individual test scores, I could have just said 4 times whatever the average was, say 70, and then plus x, that last score, and then divided that by 5. Here, since they gave me the individual scores, I can just add them up. This is a pretty common question in a bunch of different courses, not just stats, and it always seems to give people a little bit of a hard time, so we wanted to take a look at one of them here. Okay, number 2. A data set consists of the ages of a group of 3rd grade students. The standard deviation of this data set is one of the values given below. Which one is it and why? Okay, let's not even look at the choices yet. Let's think about what the ages of a 3rd grade group of students are going to be. 3rd graders are all very close to the same age. Right? In fact, if you found the average age of a group of 3rd graders, everybody would be that same age or maybe 1 year off. The youngest or oldest kids in the class still aren't going to be more than a couple years away from that mean. But almost everybody is going to be that age or only 1 year off. That means the standard deviation's got to be very small. It's got to be something, maybe between 0 and 1, because that would be the typical difference between the data values and the mean. So in sets like this, we can actually say, hey, I know the standard deviation should be small, maybe 1, maybe even less than 1. Let's take a look. First one, 8.6. Well, that's not even close. That's way too large. So let's get rid of this one. A standard deviation of 8.6 years means you're going to get data values that are maybe some of them close to the mean, but you're going to get data values that are 8, 9, and 10 years above and below the mean, and beyond that, because there's going to be data values that are well more than a standard deviation away from the mean as well. So there's no way third grade students are going to be, 8, 10, 12, 15 years away from the mean. B looks good, 0.8 years. We were talking it's got to be a small value because most of the students are going to be close to the mean age. So I'm thinking that one's it. And then look at this one. This is negative. Standard deviation can't be negative, so that's out. It's got to be B. So I'm going to say, it says which one is it and why. The standard deviation would be small since the ages would all be very close. They'd all be very close to the mean age, so it's got to be a small value. Right, most data sets, it's kind of hard to know what the standard deviation might be. Like if it said, hey, what's the standard deviation of the weight of a dolphin? I have no idea what that is. But in a set like this, where all the data values are pretty close together, the standard deviation is going to be pretty small. All right, let's take a look at the next one. Okay, a lot of words there. You got to avoid using the stare technique. Stare technique is where people just get intimidated either because of how many words there are or once they start reading it, it seems too difficult. They just kind of stare at it and hope it's like a magic eye and the answer just pops up. It's not going to happen. So let's take a look at this. Two of the variables in the student survey data mini-tab file, which is in our course info and document folder, are the age of the student's vehicle in years and the odometer reading in miles. All right, we're given that the mean age is 5.615 years with a standard deviation of 3.070 years. The mean odometer reading is 67,886 miles with a standard deviation of 44,313 miles. Which data set shows more spread or variability? Why would standard deviation not be a good choice for comparison here? And what should be used instead? All right, so standard deviation is not a good option here because the age in years and the miles on the odometer are very different data sets measured on different units and different scales. There's going to be a huge difference in miles compared to a difference in age. So looking at something like range or standard deviation is not really going to be a fair comparison. What we want to do when we have two different data sets like this, or even if it's like the same data set but measured in different units, like if one data set is heights of a history class measured in inches, and then the other one are heights of a math class measured in centimeters. Well, centimeters is a smaller unit. You're going to get more differences in the centimeters than you are in the inches. So here what we want to do is say, nope, not standard deviation, but let's use that CV, the coefficient of variation. Okay, so if we use this CV, basically what you do is you just take your standard deviation and you divide it by the mean. Some people use that as the formula, others multiply by 100% to turn it into a percentage. This is the formula the book does. Minitab will take it and multiply it by 100 to turn it into a percentage. All right, so let's take the years. All right, so if I take the years and take my 3.070, which is the standard deviation, and I divide it by 5.615, we're just going to kind of round this off. Let's see, let me punch this up. I'm getting about 0.547 for this. Or if you want to turn it into a percentage, about 54.7%. What that basically is telling me is the standard deviation is about 55% of the mean. Now let's do the same thing for the odometer reading, the miles. All right, so the standard deviation was 44,313. We're going to divide that by the 67,086. And again, if we just kind of round this off, I'm getting like 6.6605. So I guess if we rounded that off, about 0.661 or 66.1%. So the idea there is the higher the CV, the more the general variability, the more the general dispersion there. So we would say the miles show more dispersion or variability. And again, the CV there, that's used oftentimes when you're dealing with two different data sets or dealing with completely different units of measure in order to compare the general variability. All right, so last one we got here. College uses a math placement exam that has scores that are bell-shaped in distribution with a mean of 475 and standard deviation 30. All right, so since it was bell-shaped in distribution, then that empirical rule applies. So it says, according to the empirical rule, we got to figure out approximately what percent score above 505, and then a couple different things. Before we really worry about answering that, let's kind of sketch a picture here. All right, so we're going to do a real rough sketch of a bell curve. Pretty lousy here, but we're just going for a rough model. So that mean of 475, that's going to be the middle value here. And typically when we do this, if we want to make, say, 1, 2, 3 tick marks, the third tick mark on both sides should sort of take us to where the graph is virtually indistinguishable from the number line. Again, my graph is pretty lousy, but by the time you get the 3 standard deviations above 3 tick marks in our sketch here, there's going to be basically the curve on the number line. All right, what I'm going to do is count by the standard deviation here. So standard deviation was 30, so let's add 30. This would take us to 505. Add 30 again, that's going to be 535. Add 30 again, 565. Subtract 30, that's going to take us down to 445. Subtract 30, take us down to 415. Subtract 30, that's going to take us down to 385. Okay, so what the empirical rule said was that if we go 1 standard deviation to each side, that 68% of the data values are going to be, approximately 68% are going to be within 1 standard deviation. So we got to kind of take advantage of the fact that the normal curve is supposed to be symmetric. So that 68, if I chop it in half, we should get 34% in each of those 2 sections. Next thing the empirical rule said was 95% of the data values appear within 2 standard deviations of the mean. So that means jumping from 1 standard deviation up to 2, we get an extra 27%. But again, it's symmetric, so if we divide that by 2, it's 13.5. So we should expect 13% of the data values to be in those 2 chunks. Now we could keep going and do the same thing. The 3 standard deviations, the empirical rule says 99.7. So we could do the difference, divide it by 2. But notice all of the values needed to answer these 3 questions are written here. So what I'm going to do is just kind of make a note here that over here we'd have 2.5%. Over here we'd have 2.5%. I know that because if 95% are covered from 415 up to 535, that only gives 5% left over. Divide 5 by 2, that's 2.5 on each side. Now, approximately what percentage scored above 505? Well, there's 505. We got 13.5 and then 2.5. So that should be 16%. So about 16% of the students score above 505. All right, so how about between 415 and 505? So 415 starting here, 505 ending here. We got that one section of 13.5 right here, and then we got these two sections of 34. So that gives us 81.5%. Now keep in mind, the empirical rule is about approximation, so we're not saying exactly 81.5%, but we expect it to be reasonably close to that. All right, last one here is different. It's not asking for a percentage, but it says if 2,000 students take the exam, about how many would be expected to score between 445 and 505. All right, let me get some space here. All right, well, we found the percentage to that in B, right? 81.5% scored between 415 and 505. 445 to 505. All right, so let's first get the percentage. Between 445 and 505, we're looking at 68%. Right, that's actually one of the values that the empirical rule gives us exactly. All right, so now we just got to say, all right, well, if 2,000 people took the exam, then I have to multiply 2,000 by 0.68. 68% of 2,000 should be 1,360. So again, that's an approximation. About how many? About 1,360 would be expected to score between 445 and 505. All right, so these are just a few examples. Make sure you take a look at the homework problems and see what kind of questions you come up with. Good luck.